Hello everybody! In this clip we will learn about the definition of a toric variety and we will see examples. We even start with an example, a very classical one, the projective plane. P2 is a variety of lines through the origin in the vector space C3. A line through the origin and the non-zero point Z in C3 is represented in terms of homogeneous coordinates as the coordinates Z0, Z1, Z2 of the point Z taken in parentheses. The projective plane is an example of a toric variety. What does this mean? First of all, we have a torus action. The two torus, C star times C star, acts on the plane as follows. Applying an element T of the torus to a point Z of the plane is defined as doing nothing in the Z0 coordinate and then T1, Z1, T2, Z2. We observe that this action has an open orbit, namely the torus orbit through the point 1, 1, 1. By definition of the action, it precisely consists of the points 1, T1, T2, where T runs through the torus. So we just obtain the points having only non-zero coordinates in the plane. That means we obtain this orbit by removing from the plane the zero sets of the coordinate function Z0, Z1, Z2. Even more, the orbit map in this point, sending a torus element to T times 1, 1, 1, embeds the torus as an open subset into the plane. These are the features of a toric variety. We have this torus action with an open orbit and the orbit map is an open embedding. Let us turn to the formal definitions. A standard N torus is the n-fold direct product Tn of the multiplicative group C star. The standard N torus is an example of an algebraic group. That means that the multiplication map and the inversion map both are morphisms of algebraic varieties. More generally, a torus is an algebraic group T which is isomorphic to some standard torus Gn. A toric variety is an irreducible variety X with a torus action and a base point X0 such that the orbit map through this base point is an open embedding from the torus T into the variety X. Observe that in algebraic geometry we always require the action map to be a morphism of varieties. Our short notation for a toric variety is just the triple, the variety X, the torus T, and the base point X0. Let us look at more examples. First we introduce the standard toric structures on Cn and the projective space Pn. Define one n to be the point in Cn having only coordinates equal to 1. Then our standard toric structure on Cn is the following. The acting torus is Tn and an element T acts on a vector Z by T1, Z1 up to Tn, Zn. Taking 1n as a base point, we have our standard toric structure on Cn. Similarly with the projective space Pn, the acting torus is again the standard n torus and the element T acts on the element Z by doing nothing in the first coordinate, Z0, then T1, Z1 up to Tn, Zn, and as a base point we take 1 n plus 1 and this gives us the standard toric structure on the projective space Pn. We will use now these standard structures to produce a lot of new examples. Take any monomorphism phi of tori. That means phi is an injective group homomorphism and moreover a morphism of algebraic varieties. Then we can produce affine toric varieties using the standard toric structure on Cn as follows. We embed our torus T into the big N torus via phi, and then pass to the closure. This gives us a closed subvariety of Cn. And now we define an action of T on X. We take our T, shift it into the N torus, and then apply it to a point of X. The result is an affine toric variety xt1n. Similarly, we can proceed with the projective space. Again, we embed our torus T into the N torus via phi, and then pass to the closure in the projective space. This gives our variety X. And the action is defined in the same way as before. We put T first into the big N torus, and then we can apply it via the standard structure to Z. So let us see how this principle of passing to the closure of a homomorphic image of a torus can help us to produce concrete examples. Consider the following monomorphism from the 2 torus to the 3 torus, sending T1, T2 to T1 over T2, T1 times T2, T1. It gives us an affine toric variety sitting in C3 by taking the closure of the image of the 2 torus under phi. And it turns out that our X is the vanishing locus of the polynomial Z1, Z2 minus Z3 squared. In fact, plugging this into the equation, we see that the equation vanishes on the homomorphic image. Moreover, this polynomial is a prime polynomial, so it automatically generates the vanishing ideal. Similar, we can go one dimension higher, look at the monomorphism of tori ascending T1, T2, T3 to T1, T2, T3, and then T1, T2 over T3. This gives us an affine toric variety X, passing to the closure. It lives in C4, and it turns out that we have a describing equation Z1, Z2 minus Z3, Z4. So in both cases, we obtained a binomial describing equation. This is not a coincidence. This is a typical feature of affine toric varieties. Moreover, we can ask ourselves how many affine toric varieties we can produce by this principle of passing to the closure of a homomorphic torus image. It turns out that we can in fact produce all affine toric varieties this way. In the projective case, that means passing to the closure of a homomorphic torus image inside the projective space. It is so that we can produce all normal projective toric varieties this way. See you in the next clip.